In this work, I'll explain how we can approximate the three-edit distance problem within a constant factor in subquadratic time. Let me start by motivating the problem for you. Both the edit distance problem and three-edit distance problem, the main motivation for them is to compare DNAs. Say there are two different species, like a hare and a rabbit. To figure out how far the species are from one another, we look at their DNAs and we try to answer how many changes are made to one of them in order to make it equal to the other one. The better example that captures the case of three-edit distance is when you're comparing two codes. Of course, you can always represent a code as a string and then compare the two strings. But if you do that, you lose some information. For example, you have a command in your code which is nested under a function. There is a nestedness between these two pieces of your code. If you like to keep that nestedness in your data, instead of representing as a string, you would rather represent it as a rooted tree. And that way, when you're comparing the two codes, you would also take that kind of information into account. All right, so let me define the problems for you formally. In edit distance, you have two strings. You want to transform one of them to the other one. The basic operations are character addition, character removal, and character substitution, all at the same cost. You want to know how many of these operations is necessary. We can solve it in quadratic time with a dynamic programming approach. We basically introduce these variables dij such that dij tells you the edit distance between the first I characters of the first string and the first j characters of the second string. And then you can iteratively solve the problem. You draw this table, you start from the top left, you fill the cells of the table one by one. At the time you reach the bottom right, that actually gives you a solution to edit distance. Three-edit distance is pretty much the same thing, except that instead of two strings, you would have two rooted trees. And then instead of the basic operations, you have node addition, node deletion, and node substitution. And then the cost for all of these operations is the same. It's a strict generalization because of the two special cases. Either for the case that the tree is a star or for the case that the tree is a path. These two special cases are exactly equivalent to edit distance. So if you come up with an algorithm for three-edit distance, you can also use it to answer edit distance problem. Okay, so let me tell you how edit distance differs from three-edit distance. Let's say you have two codes. One of them is shown on the left, the other one is shown on the right. And they're both basically a bunch of nested for loops. For the first code, you always start with a block A and end with block C, or start with block B and end with block D. And basically, you alternate between these blocks. For the other code, you start with block A, end with block D, or start with block B and end with block C. Now, the part that I leave to you as an exercise is that if you represent these codes as a string and then compare the two strings, you would think that the edit distance of the two codes is very small. Whereas if you represent them as two rooted trees, it turns out that you need a lot of operations to transform one of them to the other one, and basically tells you that the distance between the two codes is large. And then if you look at the codes, you would realize that really the distance is large. So for the case of codes, it makes much more sense to represent your data as a rooted tree. There are a lot of algorithms given for three-edit distance. The first one starts with n to the 6th, then n to the 4, and n cube log n, then n cube. Recently, there is a work that for the unweighted variant, it goes below cubic time. So the runtime they give is n to the 2.95. On the approximation front, there is a bunch of works that run in quadratic time. The best one has approximation factor 1 plus epsilon. And also there is a near linear time algorithm that has approximation factor root n. We would like to go below quadratic time for these problems because of a lot of motivations. For example, there are billions of characters in a DNA, or gigabytes of data in any antivirus program, or there are millions of posts on social media. So running a squared time algorithm for these examples wouldn't be necessarily practical. This slide summarizes the progress on edit distance. In subquadratic time, the best approximation we could get was n to the epsilon, that this was improved to 2 to the root log n, then polylog, and in recent years we got to constant. On the negative side, we knew we couldn't solve it exactly in truly subquadratic time. Now we know even getting 1 plus little o of 1 is impossible. The algorithm that gets the constant factor has 3 steps. In the first step, we reduce the problem from the 2-string case to multiple strings. In the second step, we use triangle inequality, and the third step, we use a method that we call nearby searching to solve the problem. What matters is that pretty much the same framework also works for tree edit distance. The only issue is step 1, because the way we reduce the problem from 2 strings to multiple strings, it only works for edit distance. For tree edit distance, everything fails. So the technical contribution that we have in this work is we introduce another algorithm, another reduction, that also works for tree edit distance. And then when we plug that into the rest of the algorithm, we are able to get constant factor for tree edit distance as well. All right, so I very briefly tell you the ideas for edit distance, especially step 1, and then I tell you how we modify that for tree edit distance. As I said, the first step is reduction. So we have 2 longest strings, s and t of length n. We break them into smaller windows. Every window is a substring of a smaller size. And then instead of focusing on the 2 longest strings, we focus on the smaller strings. We want to find the pairwise distance between them. For example, these are the 2 strings. We introduce the windows. They could overlap. Then we put the windows of the first string on the left. We put the windows of the second string on the right. And we look for this matrix. So basically, this matrix tells us what is the edit distance between every window of the first string and every window of the second string. Why does it matter to find it? Because once we compute this matrix, then we could run another dynamic program, which is pretty much similar to what I explained to you earlier, except that this time, instead of going character by character, we go window by window. So we iterate over the windows. We try to map the windows of the first string to the windows of the second string. Every time we map one pair of windows together, we have their distance in the matrix. So we can incorporate that into our computation. Turns out, because the number of windows is smaller than the length of the strings, the runtime of this DP is subquadratic. So really what matters is computing this matrix, and that we do in steps 2 and 3. For tree edit distance, there is also an extra step 0 to just represent the tree as a string. I'll explain that to you with an example. It's very simple. So we start with root. We put an opening and closing parentheses with the label of the root. Then we go to its children from left to right, and we recursively repeat the same thing. So for the first child, we do the same thing, and then we go to his children, and we move on. And then we go to the second child, we do the same thing, we go to the third child, and so on. Now we have a string of opening and closing parentheses. Every basic operation would be either we delete one of them, one pair of them, or we add one pair of them, or we relabel one pair of them. All right, so I'll begin by telling you why the previous algorithm for edit distance doesn't work for tree edit distance. The first issue is that the windows are not strong enough to give us a solution. And the bad example is the following. So suppose you have a bunch of nested open parentheses. The way we make the windows, if we do it for this case, except for the middle window, all the other windows would either have the opening parentheses or closing parentheses, which makes them pretty much meaningless. If we don't want to do this, then we have to introduce large windows. For example, for the red parentheses, we need to have a large window that contains both of them. But that kills the whole idea of reducing the problem to smaller windows. So our remedy is a notion that we call super windows. So it's basically a combination of two windows, one window on the left, one window on the right. And then we merge them and we call it a super window. And then in our solution, we take into account both windows and super windows. We make a bunch of windows, we make a bunch of super windows, and then compute the distances between them. And in the end, we put these gadgets together to construct the solution. The second reason the previous algorithm wouldn't work is because we have to make our windows adaptively. So previously for edit distance, we wouldn't look at the strings for making the windows. We just made the windows before even reading the input, and then we would use those windows in our construction. We cannot do the same thing for tree edit distance because of this example. So for example, the string you see on the screen, the matching, if you want to make a super window out of the first part and the last part, the matching right part of the super window should be at the end of the string. Now, I changed the string a little bit. Now this time the right part of the super window comes a little bit closer. And then there are many other examples where the right part comes closer to the left part. And I guess what this is showing is that we cannot decide about this before reading the strings. We have to first look at the trees, look at the strings, and then decide about the windows and super windows that we are making. So we have to do everything adaptively. All right. So in the rest of the slides, I'm going to tell you a very high-level idea of how we make the windows and super windows. So the first thing is that we introduce a bunch of parameters. I'm not going to bore you with the value of these parameters. What matters is that in the end, we set the parameters in a way that the runtime is going to be truly subquadratic. The first parameter is gamma. So the way we construct the windows, we introduce a bunch of milestones, and gamma is the distance between consecutive milestones. We have W mean, which is a lower bound on the size of the windows and super windows, and W max, which is an upper bound on the size of the windows and super windows. Based on these two, we introduce a bunch of ranges or intervals. The first range is W mean to W mean times 1 plus epsilon. The second range is from W mean times 1 plus epsilon to W mean times 1 plus epsilon squared, and then we go all the way to W max. All right. So the way we make the windows is we first fix a milestone, and then we fix a range for the size of the window. We find a valid window that starts before the milestone, and the size of that window is within that range. If there are multiple options, we choose the one that starts the latest, and again, if there are multiple options, we choose the one which is shortest. So for example, if we go for the first milestone and for the first range for the size of the window, that would be our option. Then if we go for a different range, it gets larger. Then every time we choose a range, and based on that range, we make our window. Now we go to the second milestone. Again, for the first range, that would be our window, and so on. Okay. For super windows, we fix three things. The first thing is the first milestone. The second thing is the range for the left sub-window. And the third thing is the range for the right sub-window. So we find a super window such that the starting position of the super window is before the milestone. The size of the left sub-window is within the first range, and the size of the right sub-window is within the second range. On top of that, the first character of the left sub-window should be corresponding to the last character of the right sub-window. Okay, so for example, that's the sub-window we choose. And again, if there are multiple options, we choose the one that starts the latest. And of course, if we change the size of the, for example, right sub-window, we would end up having a different super window. Okay, so this is the way we construct windows and super windows. From here on, it's gonna be pretty much the same as edit distance. Again, we list all of the windows and super windows of the first string on the left, all of the windows and super windows of the right string on the right, and then we have a matrix. Every row of this matrix corresponds to one window or super window of the first string, and every column corresponds to window and super window of second string, and the entries tell us the edit distance between them. In step 2 and 3, we find this matrix. We lose a factor of 3 because of triangle inequality. But then once we have it, we can again run dp to approximate the tree edit distance value. The dp is different because this time we are not just aligning the windows, we are also aligning the super windows. So the dp instead of 2-dimensional is 4-dimensional. That brings a little, some more complications. But roughly the idea is the same. And again, we lose 1 plus epsilon in solving this dp, but because we lose a factor 3 in the step 2, and the overall approximation factor we get is 3 plus epsilon. Okay, so with these ideas, we can get 3 plus epsilon approximation for tree edit distance. The runtime is truly subquadratic. It's around n to the 1.99. It's pretty close to quadratic, but smaller than that. And the way we obtained this was pretty much we alternated step 1 to get a new algorithm. I want to wrap up by just mentioning one question that seems to be the obvious next step. The next question is about linear time algorithms. We know that for edit distance in linear time, in near linear time, we can get constant approximation. The best we know for a tree edit distance is root n. So there is a lot of room for improvement. Maybe we can start with getting n to the epsilon, polylog, and finally figure out whether we can get constant or not.